with those? Were those made incorrectly? Do you have an inappropriate chemistry for them to move? The release of the synaptic vesicle into the synapse. So far we have 3 ways to affect getting the signal. Binding of the neurotransmitter. So the neurotransmitter has to bind at the target. Are there enough receptors? Are there too many receptors? Are there too few receptors? All of that affects the signal. Reuptake of the neurotransmitter. You release neurotransmitter here, but ultimately excess neurotransmitter is going to be taken back into the synaptic terminus. That can happen either from directly at the terminus, or it can diffuse away, be picked up by astrocytes, and be returned. So we have reuptake and diffusion. Sodium and potassium channels. These are going to be sodium and potassium channels all through here. Do you have enough? Do you have too few? Do you have too many? Calcium channels. Calcium channels are critical in the synaptic knob, because without calcium channels, you will not release the neurotransmitter. Repolarization events in the target. Can you repolarize properly? Or hyperpolarization events. Do you have prolonged periods where you are hyperpolarized and can do nothing? And finally, the production of a metabolizing enzyme to remove any neurotransmitter from the synaptic cleft. So, just in coming up with a rather simplistic view here, there are 11 events, if we divide up sodium and potassium, 12 events, that it can affect getting a signal from the neuron to the target. That is one of the complexing problems with determining how to deal with a neurological issue. Which one of those 11 events do you target? Because the outcome of all 11 events is the same thing. You either don't have a signal here, you have too little signal, or too much. But the problem is, how do you intervene to change the signal? And a lot of times, there's no way to determine that. So you have to do some footwork. Now, an issue within here that's covered simplistically as binding of a neurotransmitter is a little more complicated. You have norepinephrine, you have dopamine, serotonin, histamine, orexin, acetylcholine. These are some of the major neurotransmitters that are getting signals moving through various parts of the brain. Indeed, through the entire brain for most of these. Within norepinephrine, there are 11 different receptors that will respond to norepinephrine. Now, with those 11 receptors, they're specific to different types of tissues. So a different nucleus may have a different type of receptor. Different tissues will have different receptors within the brain. Dopamine, there are 5 different receptors. We'll talk more about dopamine receptors in a minute. Serotonin. Serotonin is interesting because serotonin levels are frequently associated with depression. 14 different types of receptors. So now you have 12 different ways to affect getting the signal from point A to point B, plus 14 different receptor targets. To my way of doing math, that's like 25 minimally different ways to affect depression, which is why with depression we have so many different drugs. Histamine, orexin, acetylcholine, it goes on and on. You have to understand that with all of these pathways, there are multiple receptor types. Now, I want to go back for a second to the picture. We look at something like this, and we see these receptors in the plasma membrane of the target. And I look at that, and I say, oh, those are microanatomical structures. And they are. But let's think about this. These receptors and the channels are integral proteins. Integral proteins within a cell are critical. Number one, they control the movement of ions. But number two, how do they get there? Who makes them? Turns out the cell makes these. And a lot of times, they're damaged. They get damaged. They get bound and can't be unbound. They have a life expectancy. This cell, this target cell, doesn't have a specific number of channel proteins in its neurolemma, and that's it. Every day, some are being replaced. Every day, some are being bound. Now, you might know somebody who was taking a drug for something, and after some time, they had to up their dose. And you go, why? Why didn't it have a similar effect? And that's a really good question, and nobody, at least I find in general, once you take an advanced class, nobody tries to explain that to students. What's happening is, you're taking a drug, it's binding with receptors. Cool. Now, if it's binding with receptors, either it's going to leave these open or it's going to keep them closed. It's going to do one of those two things. If it's open, this cell all of a sudden is getting more chemical than it's used to. If it's closing them, the cell isn't getting as much chemical as it's used to. If it's not getting as much chemical, what's the nuclear response going to be? Oh, I mustn't have enough receptors and channel proteins. And what's the nucleus going to do? It's going to make more. It's going to code to make more. And you're going to put receptors out into the plasma membrane. Plasma membrane is very fluid. It's always changing. You're adding to it. You're taking away from it. And in the process of putting new receptors out, all of a sudden, what does your dose of drug do? It's not having the same effect. Because your initial dose of drug was for these 5 receptors. Now you have 10 receptors. I need more drug. Yeah.
How long does it take for the new receptors to come through?
You know, that's a really good question. You could probably get a degree figuring that answer out. The answer for that is probably highly variable depending on the individual. Now, the genetics of making receptors is fairly simple and straightforward. You have 2 genes responsible. Let's say the dominant form makes the receptor. So you have a dominant and a recessive. You make 10 receptors. You have 2 dominants, you make 15 receptors per given time. You bind those 15, and the mechanism of making receptors speeds up so that you make more, place more. So I don't have a good day response for you, but what you see when people take neurological drugs frequently is that you'll start taking a drug at a certain dose, and in 2 or 3 weeks, that dose will be adjusted. So 2 or 3 weeks, there's a noticeable effect, typically. And once again, it's variable between people because of our different genomic makeup. And yeah, so if I was to make an educated guess, I'd say a couple of weeks.
What about like when people do really, really bad drugs like meth? It's not, the come down isn't from receptors.
With meth, so you're going to take a drug that's going to cause you to really crank out dopamine. Okay? The whole thing with something like methamphetamines and amphetamines in general, is that your dopamine's just being used at like this. Like normally you're cranking dopamine, and now all of a sudden you're really just utilizing it. The coming down part is that you've released binding, but you've exhausted dopamine, so that not only are you not getting the reward, you're also not, you don't have enough dopamine for maintenance. Now, early in the semester, we talked about the lab rats that were hitting the levers, you remember, and they hit so many orgasms, they died. Okay, that was more or less that area around nucleus accumbens. What they were doing was crystal meth on steroids. They exhausted their dopamine, and you just, in this, the pathways in the brain, and this is the problem with crystal meth, you can exhaust dopamine. You exhaust dopamine, you're going to die. That's pretty much the bottom line. Also note, many of these drug users start to get jittery. Okay? Oh, dopamine, movement pathways, jitter, the spastic movements. It all will start to make better sense to you by the end of the day, maybe, or if not, by Wednesday. So, that answered that a little bit?
Yeah.
Okay, cool. So, yeah, a lot going on. Well, here's I was trying to give you this view over there. So I can get rid of my pathetic drawing, and we'll do this. So over here, we have this coronal section through the brain. This is the right side. Here's the thalamus sitting over here. Here's caudate nucleus. Here's putamen. Here's globus pallidus, subthalamic nucleus, substantia nigra. Okay? And all of the signals coming here from the cortex are excitatory. Signals coming from substantia nigra modifying this are excitatory and inhibitory. Signals coming from the thalamus over here are excitatory. So the whole movement of signaling coming through here is excitation to the striatum, if we want to put it that way. Now, we have pars compacta involved with the signaling here. Now, the signals coming out are coming out from the globus pallidus internal section and the pars reticulata of substantia nigra. Look at these signals. What are they? Entirely inhibitory. Entirely. All this can do is inhibit. Inhibition of movement is critical to movement. Without inhibition, remember, go back to thinking about the motor homunculus. The motor homunculus is very, very gross. It shows you an arm, a leg, whatever. Okay, and there are individual muscles within that. But the signal from the motor homunculus for a given muscle is move it. Do it. It's going to take it to the extreme. There is no speed control. The signal coming from that motor cortex is either pedal to the metal or nothing. Now, you know that's not what you do. Most of what you do involves some degree between them. And a lot of that is coming from signaling through this area, from the thalamus and from the basal ganglia. I've spent whole lectures on this slide. I find this slide is one that creates a tremendous amount of confusion for students. And so I've learned to take my time with it. essentially